Welcome to our last keynote today, and it's my great pleasure to introduce my colleague in the Statistics Department at Berkeley and also the incoming Director of BIDS. So I think Fernando actually needs no introduction, but I'll do a short one. So when he was a graduate student, he invented the IPython and later became a co-founder of the project Jupyter. And he got this with his team, the big award, the ACM Software System Award. And the past awardees include Java and Unix, so you go figure. So without further ado, you get Fernando.
First, I want to thank Bin and Russ for putting together this amazing program. I had to skip out for one or two BIDS-related duties today, unfortunately, but I've seen a number of talks and they're amazing. And it's wonderful. BIDS was a space that was created about 10 years ago when a lot of these discussions around openness and reproducibility were still somewhat debated. And it's wonderful to see that now it is a field that can convene an actual engaged intellectual audience with work from multiple places. And it's fantastic to have the honor of hosting something between Berkeley and Stanford in this space. I've known Russ for a long time. We've talked about these ideas for years. Obviously, Ben and I kind of hang out down the hall on the fourth floor of Evans. And so it's wonderful to welcome you here and to see this coming together. I really hope this will be the first of many such events. And we want to make BIDS into a bit of a home for this type of work and these types of ideas. Open source, open science, as well as the role of ideas around AI and statistical learning in science and society as a concern that impacts all disciplines and not only computing. But with that context and my gratitude to both of you and the entire organizing team and the staff and volunteers who have helped, let me talk for a few minutes about Jupyter, starting with a quote that, has this quote already shown up in any talk today? Because it's almost obligatory. It hasn't. Okay, this is a Stanford quote. This is from colleagues of Russ's in stats and geoscience. And it's kind of the classic quote on reproducible research. I've used it hundreds of times in talks of mine, and I think it captures perfectly, with perhaps the added twist these days that if we actually want to make research reproducible, perhaps we also want a way to run the code, because simply describing it may be a little bit too much. This was written by Claerbout and by Bucket and Donahoe, paraphrasing John Claerbout in 1995. It's an old quote, but it has been, in a sense, the guiding light of thinking for many of us in this space. A lot of the discussions today have been around statistical reproducibility, and I think that's an absolutely fundamental topic. I'm going to switch gears a little bit and talk about the perhaps easier part of that question, which is a little bit of a discussion more centered on the computational reproducibility aspects, even though what I'll be telling you is a quick story about a course that is officially in statistics. And it's a course called Collaborative and Reproducible Data Science that I've taught a number of years. I didn't start it. It's a course that tries to kind of ask questions about the why, the what, and the how of making science more reproducible, simultaneously more open and collaborative. And I think those ideas all interplay with one another. So it's a course where, first of all, we try to frame the idea of science being more reproducible, more open, and more collaborative as an essential concern of all modern computational research. And I would argue these days you can kind of strike the word computational because it's a little bit unnecessary. I know of very little research that's left today in the world that doesn't have computing somehow embedded in it, about the social and scientific implications of reproducibility or the lack thereof. And we try to frame the problem kind of in multiple perspectives: practical one, ethical ones, and epistemological ones. And we, after kind of working through some core ideas, we try to spend our time in building the skills and fundamentally habits for working in science a little bit differently, so that these questions of reproducibility are not a publication time concept, right? It's not when the editor kind of bugs you that you kind of scramble to bundle together a bunch of things into some incomprehensible bag of files in a zip archive and shove it into supplementary materials. But no, it should be a practice because the process is what makes things better. So this course was originally designed by Professor Philip Stark, also in our department, and I picked it up and I've taught it with a number of TAs. In particular, I would encourage you to talk to Facu Sapienza, who is here in the room, statistics PhD student who just graduated and is actually now going to be a postdoc at Stanford and has been my GSI for 2 years. We worked together on this. It's a course that combines lectures and lab. We offer it as a mixed class. And I want to tell you a little bit of how we've worked, kind of what we've learned and the approach we've taken in this class, because it may be useful to you. All of our materials are openly available online. They're all on GitHub, obviously. And I have actually seen reports of other entities and institutions trying to build courses like these, and perhaps with mixed success or not very good experiences. And for us, it's been fantastic. It's been really successful. And so maybe there's something in what we've done that may be useful. These are enrollment statistics from a couple of editions, the 2017 and the 2021 editions. And as you can see, even though it's offered as a statistics course, and the majority of the enrollment comes from stats, computer science, and data science, we also have a ton of people from all over campus, and that's really interesting. I end up in PhD thesis and qualifying committee exams for all kinds of places on campus because of this class. Students in architecture take it, and civil engineering. I've learned about modeling of stresses in buried pipelines, and about air quality, and about nuclear reactors because of this class. It's a lot of fun. So as I said, on the one hand, we do try to have a thread through the course of ideas around why reproducible research, the crisis of reproducibility, some case studies, and some reflections on this topic that are the basis of weekly discussions that happen during lecture, and that tackle more of the philosophical framework and the social implications of reproducibility or lack thereof in modern science. A lot of things that have already been at least discussed or hinted at in presentations today. But the bulk of the course is actually in building a set of focus on building a set of skills where we kind of try to map for the students that there's a bunch of ideas that are really important in modern computational science. The specific implementation we happen to use, that may vary, that may change. We make opinionated choices. I'm a Python person. The stack I know best is kind of the Python Jupyter stack. You can do these things with other tools. That matters a lot less, and some of these tools will change over time. That's inevitable. The notion that if you're doing computationally heavy research, you should have version control, you should script your analyses, you should automate all you can in a predictable way, you should think about the steps of your data analysis process, you should include testing and documentation as an integral part of your workflow. All of these should not be optional in modern computational research, right? All of these things really need to be fundamental skills that you pick up along the way. And by the way, they'll help you get a job if you end up in industry, all of them. Now, the first one is computational hygiene. It's a lot better to brush your teeth every day than to get a root canal. It really, really is. None of us needs to be told to use a toothbrush every day, I hope. You shouldn't have to be told to use Git every day, right? Git is the toothbrush of computational science. Please brush your teeth, right, every day. And the way we make our students brush their teeth is by teaching them Git once. The first lecture of the course is about Git. We don't teach commands, we don't teach error messages, we teach concepts. Git is not a version control system, by the way. If anybody told you that, that's a lie. Git is a system for manipulating graphs. It's a system for manipulating graphs, and if you understand it that way, and that can be explained very simply, we have pretty pictures to explain it, everything makes sense and everything is very straightforward. Once you understand that, and then it turns out that your class runs on GitHub Classroom, so every single week you're turning assignments, you're doing homework, you're doing projects, and everything happens on GitHub. By the end of the semester, it's just another thing you do. You'll learn to brush your teeth, right? And we also teach them other benefits of this. The life reproducible with Git. How do you manage your entire system configuration by having your computing environment and your home directory skeleton set up on Git, so that when you land on a new computer in the cloud, it takes you, 2 minutes to be up and running in the environment you need, because you open the thing, you go to the one repo, you copy a command, you type it, and boom, you're done. And every time you land on a new system anywhere on the planet, you're up and running in 2 minutes with all the tools that you expect and with the environment that you need. That means you learn how to manage dependencies. You learn the concept of managing dependencies, that software has dependencies and there's ways to manage that in a civilized and organized way. We've advanced. This is not 1995 anymore. We have tools to do this better, and those tools have been well adopted. And so if you learn how to use them, none of this is magic. Life is better. We take lessons. I don't know, Titus, did you write some of these originally? No? But Titus was one of the early proponents of the notion of testing in the scientific world, right? And folks from the carpentries have developed wonderful lectures on automation and testing, and we reuse those materials. This is about open source, and so we don't reinvent wheels. We don't have to. I encourage you to rely on the wonderful open materials from the Software Carpentries project that has lots of really useful stuff for science. Students learn kind of a standard workflow, right? When they're doing a project, everything has a make file. Everything has an environment YAML file. And with that, right, they can run the analysis to make the figures of their code. If they need to check something, they can just type make, and the figures get done, graphs get rebuilt. Not absolutely everything in life has to be done this way, but if you learn and you realize that these things are much easier than they seem, that you don't have to be a software engineer building massive systems at Google to do these things, but that to make your paper, to do anything in your daily life, it takes 2 seconds to do one of these things, and you learn a couple of tricks like how to make targets that are self-documenting and whatnot, life is actually easy, right? Then when you're going to share your work, you publish it, and you make it from the get-go. You can build your work in a way that your original analysis can be shared with others. The stack that we use obviously is based on Jupyter, so we teach them how to work with the tools in Jupyter Book to make interactive, live executable documents that are built out of the original sources in Jupyter. And I'll talk again a little bit later about the technology, some recent improvements on the stack that have come around recently. Then, if you actually want to share the actual work, it turns out that we've also figured out how to do that. This is, again, something that came from the world of neuroscience originally. I don't know, Russ, if you know that the original version of Binder was developed by Jeremy Freeman from the Howard Hughes Medical Institute, ex-neuroscience researcher who did amazing work in fruit fly brain research. And we had a conversation here in Oakland, 2014, 2015, talking about how we kind of had the pieces with Jupyter to be able to kind of open a Jupyter container in the cloud, but it was annoying if you wanted to run it with anything but some demos that we had for Jupyter. And that would be neat. If only you could open that container that had Jupyter, but you could also open it with some other Git repository. And you could load the dependencies for that Git repository. And Jeremy calls me 2 weeks later, like, hey, I made this thing called Binder. Why Binder? Remember that first quote from Donahoe and Buckheit about published papers being the advertisement for a paper? Well, think of it like when you're buying a house, right? The advertisement for the house is the little like printed glossy one-pager that the real estate agents put outside. The thing you really want to see is the 3-ring binder from the home inspector that tells you whether the sewers work, right? And whether the AC and the furnace are going to have to be replaced in 2 years and whether the roof is about to collapse. That's what you really want to know. So this is the 3-ring binder for science, right? And the 3-ring binder for science is if you have a repository, it could be on GitHub, it could be any version control repository, that has a collection of Jupyter notebooks or Python scripts or Quarto notebooks, and you provide your dependencies explicitly and in a machine-readable way, then the machines can do the work for you. Because people have figured, and you don't have to be a cloud engineer. If the words Docker and Kubernetes are gobbledygook for you, good, that's fine. You're a scientist, you don't need to know that. All you need to do is if you learn to put your work in a place where it's well written, well documented, and you told some piece of equipment what dependencies your code has, a machine can pick it up and a machine can package it and bundle into this thing called a Docker container, and then it can shove it into through this thing called Kubernetes into the cloud, and it can run on a deployment of Jupyter Hub that has been customized to open up in a live executable instance with all of that. This takes actually a fair amount of work. I mean, Jeremy's first version of Binder was written in 2 weeks. It's been years of development to make this like a global distributed federated network. We got funding from the Moore Foundation eventually. It's been a lot of work. But fundamentally, this is just technology that works and that then we can adopt. Students also learn that, hey, if the machines can do work and I can automate things, maybe the machines can do the work automatically for me. So GitHub has this wonderful thing called GitHub Actions. GitHub Actions are things that once you've gotten used to using GitHub, then it's one more, and you've gotten used to automating things, it's one more little thing to just add these few little files in your Git repository that say, hey, when I do this, you do that, right? They already had the concept of dependencies, of things depending on one another, of asking, do this at the command line with make. This is one more thing where you just say that implicitly. Whenever I do something with Git, you machine up there, do something else. GitHub Actions is a system that allows you to declare actions that happen in the cloud to the code in your repository based on criteria that you specify. They can be extraordinarily complicated and sophisticated. You can effectively, half the internet runs on this kind of systems these days. But at the end of the day, it's pretty simple. They don't have to learn a lot. They have to realize that the basic ideas are easy to learn and useful, that some everyday things that are actually practical in science can be done with this, with basically copy-pasting a couple of things, and that's about it, right? And that there's potential. So if one day they need something deeper, they can go down the rabbit hole as necessary. And for example, when we commit, I used to make changes to lecture materials about a minute before lecture, right? And then walk up and plug in my laptop. Why? Because I would do that, and then a GitHub action called build the pages and deploy would run in about 30 to 40 seconds to a minute. Right? The variability was between 30 seconds and a minute. So I knew that between the time of me committing, walking up, plugging, the student sitting down, the website would be live, and everything would be ready to go. So I could work on my laptop, type git push, begin plugging the laptop, and everything would work. GitHub would grab that, deploy the book, put it on the website, da-da-da-da-da. And it turns out that when we do this, the instructors can work in the same way. At Berkeley, we don't run, so this course doesn't run on their laptops. We'll come back to that point later. The course at first runs in the cloud entirely. The students log into the cloud because at Berkeley, we have this organization on GitHub called Berkeley-DSCP-Infra. Eric Van Dusen is in the room. He's one of the people responsible for all of this. His team is amazing. And there's a repository called Data Hub. This repository has a directory called deployments. If you click on that, that deployments directory has a lot of subdirectories that have names like Stat159, R, Prob140, iSchool, X, Data X8, X Data 8, X version 2, Data 8, Data 102. These are courses for which an entire hub in the cloud has been specifically configured with the library versions, with the dependencies, with everything to run a course. These hubs serve on the order, and Eric will correct me if I'm wrong, of I believe about 10,000 users a month on campus. There's about 25 different URLs. Each of these names corresponds to a URL, .datahub.berkeley.edu, so students know. By the way, if you didn't know this, if you have a CalNet ID, if you're Berkeley staff, faculty, or student, if you have a CalNet ID, any of these names, .datahub.berkeley.edu is an address you can log into with your CalNet ID, and you have a hub that's pre-configured for you, that runs in the cloud, and that has all manners of tools for research and education available. They've been pre-configured mostly for courses, but we're thinking of expanding that in the future. And the system is amazing. We as faculty make changes to the course. I need a new library, I need a new version. I go on GitHub, I change a version, I make a pull request, I merge it in when it's ready. The systems check it. I get a hub in the cloud that's been deployed, a testing copy that's been deployed with my changes. I go play, and when I say it all looks good, the team then pushes those changes into the production version that they only control. Fantastic, right? We run an entire university like this. We literally run, I don't know, how many courses are running these days? 60, 80? How many courses run? Yeah, 60 or 80 courses run on this on top of 25 different hubs, all in the cloud. And so this gives the students a hosted installation that has these addresses like stat159.datahub.berkeley.edu, where they click on this button that says sign in with the campus authentication system, bCourses, and they log in, and they see something like this. What is this? This is Jupyter Lab. But importantly, what this gives them, is something that can also run on their local machine, regardless of their operating system. And we do teach them that. We do teach them how to take this home, how to customize it. We don't do it on day one. We start in the cloud when everybody works the same, where all they need is a keyboard and a screen, and where we also, by the way, that has a really important democratizing effect, which is it doesn't really matter the quality across economic differences, across the quality of hardware that students may or may not have, the student who has a very fancy laptop, the student who has more limited means and has an older broken one. At the end of the day, not a big difference because it's just a keyboard and a screen. And we know that they all have access to the same computational resources. But it is important over the course of a semester that at some point on a course like this, students who may go on to research have their own tools. So halfway through the semester, rather than doing tech support on day one and paralyzing the class on tech support and debugging issues, halfway through the semester, one of the labs is, okay, you install these tools on your laptop just as an exercise, right? The course continues in the cloud, but you do learn how to do that on your system. If you hit a rough patch, Facu will help you, we'll try to debug it for you, but that does not block the evolution of the class. And importantly, they learn that through this cloud environment, because we built Jupyter Lab this way, they get a real computer. This is not about Jupyter Notebooks, by the way. Notebooks are a piece of the story, but Jupyter Lab is a complete architecture to access data, to access files, to edit markdown files, to edit LaTeX files. It's a complete computing system in the cloud. They learn how to use Make. They learn how to use the terminal. They learn about file systems. Some students arrive only having only had as their computational experience some combination of iPads and Chromebooks. And so they're not really familiar. Those are systems that completely abstract away the notion of a file system and a normal computing environment. So here they get access to a real computer. This is not Colab, the Google thing. This is a real computer with real file systems. And we also add a thematic thread in the course, which is the theme of Earth and climate data. We typically invite Dr. Shel Genteman, one of my heroes, a scientist at NASA who lives in the Bay Area and works on both open science and oceanography, so that they also get a taste, because the course is grounded on working with real data, real scientific problems, and we don't emphasize as much the questions of statistical reproducibility and robustness that have come up today, but we do work with real data. And first of all, I want our data science students to learn about data that's grounded in causal models, as Michael was saying this morning, Stephen was saying this morning, grounded in true causal models, by which I mean ODEs and PDEs of physics, right? And second, that the modeling tools that they're learning apply to these other concepts, in addition to being an opportunity to learn that there's also life beyond CSVs, right? There's more than a data frame in the world. There's these things called n-dimensional arrays and tools like Xarray and ZAR and other tools that are necessary for manipulating other types of data. So they learn how to practice on that. And one of the projects that they have to do is grab the last paper that Shel wrote, which incidentally is about heat waves in California, in Northern California, so it's very locally relevant. The last paper she wrote before she kind of got the religion and started using Python. So it was a paper that was published. She put the code available as a collection of MATLAB scripts. And so they get kind of the moral equivalent of email the author, right? And here's the code, good luck to you, right? What we do is Shel gives a talk, they have the paper, right? And they get a repo that has a collection of MATLAB scripts they cannot run, because we don't have MATLAB on the hub. They can look at the code, but they can't run it. These are non-oceanography students. They work in groups of 4, typically with one grad student and several undergrads, and their task is to reproduce, scientifically replicate the key figures of the paper. Not pixel perfect. We don't have access to the raw data, and it doesn't matter. But can you produce figures from which you would derive effectively the same conclusions? You would draw the same conclusions from these figures if you have access to the base data. And it's a fantastic experience. They absolutely love it. It's amazing. They all manage to do it. They work hard. They work super hard, but they manage to do it. And towards the end, we kind of wrap it into what effectively I kind of like to think of a standard playbook for building a scientific story that has one main narrative. It could be a tech file. I mean, we do it with notebooks, but honestly, this could be a tech file, a markdown file, a Word document for all I care. You typically, when you have a scientific story, the order in which you tell the story should not be, and rarely is, the order of the computations. So the notion that you're going to write one gigantic notebook that's going to be both all of the analysis and the paper is wrong. What you should have is a notebook that summarizes and tells the story driven by the scientific questions, but that has very little code itself. It mostly pulls results. Those results should be generated in analysis notebooks that are included in there. The data should be either included if it's small or linked if it's too large, and we have some discussions on data sharing and ways of sharing large-scale data sets. They also learn to develop a package. They learn a little bit about packaging, so they have to include a bit of the code that is in a standalone, self-contained package that can be pip installed, and that includes reproducibility support, as well as good practices such as a README, licensing, etc. We discuss issues of copyright and sharing and so forth. And so this is the kind of thing that they do. Those of you who have been in the Bay Area for a few years may remember that this is not a special effects image. This was our life. This was a picture taken on the Bay Bridge during the heat wave of 2019, 2020, I don't know, pandemic years, I forget. This is an example of one of the projects that the students turn in where the main document was about analyzing air quality. It's mostly written as a scientific article, right? The bits of code that have are very little. Display an image, right? Just display a figure. Mostly diagrams, figures, equations, references, and analysis. And then there's the analysis notebooks. The supporting notebooks are there. And the supporting notebooks, those guys do have all the GORP details, right? They have all the details. They produce the graphs. They save the outputs. They're the ones that get run by makefiles. And then there's also a little package that is the supporting code. And the supporting code has to have documentations. It has to have tests. It has to have unit tests. We have to see that the tests run. And all of that has to be in a Git repo that has to have a binder button so that we can click on that and then we can launch into a live version of that analysis. And it turns out that students can do this. So when scientists say that this is too hard to do, I say, wrong, because I know that Berkeley undergrads can do it, right? The student feedback has been always more or less uniformly very, very positive. Students love it. Students learn, right? Some students have actually started contributing to open source after this class. That's not necessarily a goal of the class, but it is a great outcome if some of them follow that route. Some of them actually have ended up wanting to do later research projects with me. And some of them have actually kind of had career shifts. Even folks who were not heavily computational, were a little bit curious about this, ended up in computing. Now, to wrap it up, to close the last section, this is a very, very schematic version of what I think of as the life cycle of computational research, if you will. You have some idea you're exploring, you start collaborating, maybe you do some runs at large scale in the cloud on HPC, and at some point you end up publishing, sharing, communicating your work, papers, blog posts, textbooks, whatever it is, right? It's very, very schematic, but I don't think entirely wrong. The idea with Jupyter is that we've tried to design a collection of tools and an architecture so that all of these steps are kind of a fluid gradation along a continuum rather than discrete steps where you have to break, change tools, toss things over a fence. And in particular, when it comes to publishing and communication, the machinery in JupyterBook has gotten really interesting lately. And this story that I've been telling about Stat 159 that began being taught in this form in 2017 is now being adopted by scientific society. So for those of you in the geospatial field, we had a wonderful talk about geospatial statistics earlier today. AGU is kind of one of our home conferences. Those of you who are not, it's the American Geophysical Union. It's basically the Earth and Space Sciences big conference. And they had an initiative funded by the Sloan Foundation, the same program officer, Josh, who funded the original work on Jupyter called Notebooks Now, to make notebooks kind of a part of the peer-reviewed publication record. And this is an example of the kinds of papers that now AGU accepts under that. And it's basically what I just told you. They are rendered notebooks, but that have, not only are they rendered very pretty and with additional stuff, that have immediately way to download, get the PDF, get the sources, launch executable versions via a binder-like resource, and they have all of the supporting documents broken down. I mean, the reason it's this way is because we participated in the design of this. It was an open process. It was discussed by the community, and we argued that this was a good model. This is now the Scientific Python Conference is now adopting the same machinery for the proceedings of the SciPy Conference. They're even back-porting old proceedings. MIST, for those of you who haven't heard, is kind of a derivative project. Eventually, in the Jupyter project, we kind of got fed up with Markdown not quite getting its act together, so we said, okay, we're going to pick up Markdown, we call it markedly structured text Markdown, and the best ideas of restructured text to effectively get like a modern version of LaTeX that actually works. And so what we have now in Jupyter is machinery that allows you to write all the things that you would do for scholarly communication in LaTeX, but in Markdown, including that in the text blocks, you can include results and values from the computation. So the document itself, not just the code results in the notebook, but the text part of the computation and the mathematics can be connected in an integral way to the computational process, and that opens a lot of really cool ideas. How do I get this to that? And so the idea is that hopefully you write once in combinations of plain and .md files with Mist or Jupyter Notebooks with Mist, and you can produce websites, journal articles, etc. from a single source. There's templates. It's really, really good work that has been done by this team. But finally, all of this opens opportunities that require new infrastructure and new tools. This is a bit of a plug for an organization that several of us in this space co-founded called 2I2C. It's led today by an ex-Berkeley neuroscientist who trained here in ECOG data analysis, but is now the executive director of 2I2C. This is an entity that serves as a nonprofit to offer the kinds of infrastructure that we had at Berkeley that I was describing. Well, Eric's team is amazing, but they're not a company and they can't run this as a service for the world. 2A2C is a nonprofit organization that does this as a service while contributing back to open source communities and while embracing the idea that has been encoded in a document of what's called the right to replicate, meaning anyone who uses these tools should have the right to replicate them on their own, even if they're buying a commercial service, right? As a principle of open and reproducible science, the user should be empowered. Now, as a quick plug, because I heard some of you are interested in science, we are bringing this kind of workflow into the actual loop of the hospital clinical care. Ask me about this if you're interested. This is something that started recently. And thank you. I think I'm at my time. Thank you so much for your attention.
Perfect on time. Questions from the audience?
I guess I'll start. So thanks, wonderful talk as always. I'm wondering what you think about AI coding assistance, both with respect to this ecosystem in particular, but also more generally with respect to like reproducibility and coding and how they may change how we think about getting people to do reproducible work.
So excellent question. Do I need to repeat them for the recording, or does the microphone go? Does that microphone go to the audio system? Okay, I don't need to repeat. So there is a module within Jupyter, a new subproject called Jupyter AI, which has been designed kind of with the idea of allowing us to access AI systems within this philosophy. So Jupyter AI is a subproject within Jupyter Lab that offers APIs effectively throughout Jupyter Lab to connect to AI agents, but where you specify which one you want to connect to. First of all, so that people can, yes, if you want to connect to OpenAI's models, you can, but you could also potentially connect to local private models. And number two, because it's integrated within the environment, it gives us an opportunity to, for example, log the work you're doing with an AI model, right? Include information about where and how the agent participated in the creation of knowledge, because I don't think we can avoid the existence of these systems. I think what we need to do is understand when and how they participated in the process. They're fundamentally, at least in the current generation, they're fundamentally stochastic nature that has where we don't really have control over things like the seeds the way we do with simpler codes, requires that we think of them in a sense. I think it is useful to anthropomorphize them a little bit in that sense, that they are a little bit like a person who, when you ask them to do the same thing twice, they do similar things, but not necessarily the exact same thing. Therefore, logging, traceability, and transparency, I think, become increasingly important. So we're trying to build in Jupyter AI tools that allow you to use an AI agent, but to have it log within the document. And this is a place where, for me, the way we thought about the internal document structure of Jupyter, which is a JSON data structure with metadata fields everywhere, becomes useful because we can log, not only visibly log some information, but also log internally metadata that can be surfaced or analyzed or post-processed later. So I think it gives us hooks. I don't have an answer. It's a really complicated and fast-evolving topic. So what we're trying to have is principles and tools that allow us to reason about the question. I don't know if it's a satisfactory answer, but that's where we're headed now. Thank you, Russ. I think there was a question.
Yeah, I just wanted to say thank you so much for this talk. You're very much speaking my language, because at least in my department we're trying to replicate this sort of thing, and reproducibility is quite important to us. I guess my question is, do you have like any tips in regards to successfully reproducing like this type of course at like say other universities? Like are the repos that you use like available to the public, that kind of thing?
Everything is public. We'd be happy to talk to you. And honestly, I mean, we learned some lessons, and Facu and I would be more than happy to talk to you. But part of the reason, and we're derelict and late and writing this up as a little article somewhere, because I have heard reports of a few institutions where this has not gone well. And I'm not sure what the specifics were. I trust that there were some local context issues that made it difficult. But for us, it has been, I mean, it's been a lot of work, but it's been really fun work and really, I would say, successful work. Like we haven't had completely blocking catastrophic problems, and the challenges we've encountered, we've been kind of able to work through them. So we're happy to share the lessons, and all of the materials are available online.
Cool. Thank you so much.
Yeah, thank you so much for a really interesting talk. I'm wondering, do you have any thoughts for us researchers that work with highly confidential data to approximate this type of reproducibility?
Yes, I think that's a really important question, and it's actually going to become even more important for us in this Jupyter Health project, because we're really talking about operating hubs in an internal clinical environment with actual individual patient data and cohort data. So now we're kind of going head into that mess. I waited a long time to do that, but I finally found the right partner. The head of informatics research at UCSF is my co-director in the project, and she knows what she's doing. So I am thinking a lot about that. I think the answer is twofold for me, at least a beginning of an answer. And I know it's a very complex topic and I'm going to oversimplify, but on the one hand, still relying on fully open source infrastructure and open source interoperable infrastructure that can be replicated with the right machinery, more or less identically. You can run a copy of it privately and a copy publicly, right? And then there's a lot of really interesting theoretical, statistical work, and we have a lot of people here more competent than I am in that, in questions on how do you generate correct synthetic data that reproduces the right distributional properties, the right structure to validate an algorithm. And I'm not talking about de-anonymized data. I have a lot of concerns with anonymizing truly confidential data, because de-anonymization, as we know, is an after-the-fact process that can be done by data completion in ways that the original authors didn't expect. So I think purely random, I mean, and I also know differential privacy experts do have tools in that space, but I think also having tools for reproducibility and validation and the issue of trust, at least being able to have good tools for the creation of synthetic replicates, artificial synthetic replicates, where you can guarantee you can validate the code, the algorithm, the sensitivity, and any statistical property that you want of the real data can be checked externally, at least gives us a start. I'm not claiming that to be a complete answer, but I think there's a program there that includes technology and statistical research that can offer some ideas. And I'd be happy to talk more or learn more from experts in the audience. But I don't want to take more of my time because I know you're running a tight schedule, so I'd be happy to chat later with folks.
Let me just take my privilege, like how easy, how much work to add stability, which a lot of us from the scientific reproducibility point of view really like, on top of this Jupyter lab.
I think of that, and I'm not an expert, I mean, we should work on that. I think of that as a process, not as a single tool. I think the pieces are there, but we have to sit down and add. And I think for that, the real question is, what pieces of asking questions of stability, validation, are map onto clear tools where they can be represented either whether it's computational elements or interface elements, and what pieces are just a human process, right? And there's probably a little bit of both, and the correct answer may vary by domain. But if there's pieces of that process where you've identified and really understood this part of the problem is kind of encodable, either computationally or in terms of UI workflow, this architecture is quite flexible. But I don't know the specifics, and that's a question that we should dig into.
So we should talk. Let's thank Fernando for a wonderful talk.
Thank you.